Assalamu alaikum dear students. In previous lecture we discussed the addition and properties of addition of two complex numbers. Now today we are going to discuss the multiplication of two complex numbers. Now let z1 and z2 are two complex numbers. Then this z1 dot z2, that is z1 into z2, this is called as the multiplication of these two numbers and is defined as z1 into z2. Now if we assume that this z1 is a plus iota b, that is real part of z1 is a, imaginary part of z1 is b, and z2 is c plus iota d, that is imaginary part of this z2 is c, while as its real part is c. Now by actual multiplication, it is a plus iota b into c plus iota d. It is simply a into c plus iota d plus iota b into c plus iota d, which is simply a into c is ac. So a into iota d is iota ad, iota b into c is iota bc, plus iota into iota, it is iota square bd by actual multiplication. That is the ac plus iota ad, iota bc plus iota square. You know that iota is simply root of -1, and this iota square is -1 by squaring both sides, which implies that here it is minus bd. Now taking iota common from these two numbers AD and BC, we simply get iota AD plus BC. Now here it is independent of this iota, minus BD is independent of iota, which simply implies that it is AC minus BD plus iota AD plus BC. Here A, B, C, D are the real numbers, that is their product, their difference, and their addition is also a real number, which implies that z1 into z2 is a real number with real part equals to AC minus BD plus iota AD plus BC, that is iota AD plus BC is simply it is imaginary part. So this means that this product of two complex numbers is also complex number. So in this way you can multiply any two complex numbers. Now the properties of this multiplication are, now the closure property you proved, from this z1 into z2 is again a complex number, which implies that the complex numbers are closed under addition, that is set of complex numbers is closed under addition, means if we multiply any two numbers we get a complex number, this means it is closed. Now commutative property or the commutative law, now you know that z1 equals z1 into z2 is ac minus bd plus iota ad plus bc. Here in the same way you can prove that z2 into z1 is ac minus bd plus iota ad plus bc, because product of two complex numbers is commutative. That is, if we have two numbers ab and bc, ab, then a into b equals to b into a. This is called as the commutative law. Similarly, this operation, that is multiplication of two complex numbers, also satisfies the associative property. That is, if we have three numbers z1, z2 and z3, then z1 into z2 into z3 here into z3 equals to z1 into z2 plus z3. Now the multiplicative identity. Now identity mean under a given operation means that element from the set which after operating does not affect or does not alter the behavior of a number. Now here the multiplicative identity, if we consider a complex number z equals to iota 1 plus iota 0, that is that complex number whose real part is 1 while as its imaginary part is 0. Then for any complex number z1, if we consider the general complex number a plus iota b, then this z1 into z2 is a plus iota b into 1 plus iota 0. Now 1 plus iota 0 is simply 1, and a plus iota b into 1 is a plus iota b. So a plus iota b is simply z1, which implies that after multiplication of any complex number, that is z1 a plus iota b with this z 1 plus iota 0, the resultant is again a number itself, This means that this z1, for this z1, there exists z equals to this 1 plus iota 0. This z1 is simply called as the multiplicative identity. Like in multiplication of real numbers, we have 1. If we multiply 1 to any real number, we get that real number. This one is called as the multiplicative identity in the set of real numbers. Similarly, in set of integers or in set of real numbers, 0 is called the additive identity, because it does not affect upon addition. So there exists multiplicative identity in the set of complex number, which is called simply unity, that is 1 plus iota 0, which is simply 1. Now the multiplicative inverse. Now if we consider z equals to a plus iota b, where z not equals to 0. Now here z not equals to 0 means the complex number whose real nor this imaginary parts are 0. So at least one should be non-zero. Then we can define the complex number 1 upon z equals to 1 upon a plus iota b. Now if we multiply this 1 upon z with this z, it is z into 1 upon z, z cancels, so we simply get 1 plus iota 0. So for any complex number z, 1 upon z is called as the multiplicative inverse, or for 1 upon z, z is called the multiplicative inverse of a complex number. So there exists this multiplicative inverse for each and every non-zero complex number. Now the last property is the distributive property. If we have three complex numbers z1, z2 and z3, then this z1 into z1 z2 plus z3 equals to z1 into z2 plus z1 into z3. That is multiplication of complex numbers distributes over addition. That is z1 into, that is we are here distributing this multiplication, that is z1 into z2 plus z1 into z3. So this was about the multiplication and its properties. Now the fourth operation is the division of two complex numbers. Now let me consider an example. If we consider a complex number 2 plus iota 3, then its inverse is 1 upon z, 1 upon z. It is also a complex number. How? Here we have a complex number is of the form of a plus iota b, but this number 1 upon 2 plus iota 3 is not in the form of a plus iota b. A plus iota b. So firstly we will convert this 1 upon 2 plus iota 3 into the form of a plus iota b. That is 1 upon 2 plus iota 3. By rationalizing this, rationalizing means to reduce the denominator. Now how to rationalize this? It is simply 2 minus 1 upon 3 into 2 minus 1 upon 3, because it will cancel, these two will cancel in numerator and denominator. We simply get 1 upon 2 plus iota 3. Now by actual multiplication, 1 into 2 minus 1 upon 3 is 2 minus iota 3. Now here in denominator we have 2 plus iota 3 into 2 minus iota 3, which is of the form of a minus b into a plus b. So it is simply a square, it is 2 minus b square, b is here iota 3. So iota 3 square is simply iota square into 3 square. 3 square is 9. Iota square is minus 1. So minus minus becomes plus. So it is simply 4 plus 9 in the denominator. Now which is of the form of 2 minus iota 3 upon 13, that is 2 upon 13 minus iota 3 upon 13. So clearly this 2 upon 13 is real, so it is of the form of a, and 3 upon 13 is b. So the real part and this imaginary part of this complex number 1 upon z, that is 1 upon 2 plus iota 3, is 2 upon 13 minus 3 upon 13. Now if we consider, this is the how to find or how to convert 1 upon z, or how 1 upon z is the complex number, or how to find the real and imaginary parts of any 1 upon z complex number. Now if we consider only two complex numbers z1 while and z2, while z2 not equals to 0, z2 not equals to 0 means for this z2 at least a or b, means real or imaginary part, should be non-zero. Then z1 by z2 is called as the quotient of the two complex numbers. Now how to find this quotient? If we consider z1 to be 1 plus iota 4, z2 to be this 1 minus iota 3, then z1 upon z2 is the quotient. So it is of the form of 1 plus iota 4 upon 1 minus iota 3. Now here we have to convert. This is the complex number, this z1 upon z2. So we need here rationalization. Now after rationalizing, it is 1 plus iota 3 upon 1 minus iota 3. That is multiplying and dividing this by 1 plus iota 3. Now by actual multiplication of 1 plus iota 4 with 1 plus iota 3, we get simply this minus 11 plus iota 7, and by this multiplication in the denominator, that is 1 minus iota 3 and 1 plus iota 3, which is of the form of a plus b into a minus b. A is here 1, b is here iota 3, so we have simply 1 plus 4. Here it is 3 square, it is 9, so 1 plus, here it is 9, 1 plus 9, which is 10, hence it is of the form of this complex number is, after simplifying, it is of the form of 1 minus 11 upon 4 plus iota 7 upon 4. So this is the quotient of these two complex numbers z1 and z2. So in this way you can find the quotient of any two complex numbers with denominator not equals to 0. So thank you.